It is 20 reasons that you want to be conformally transforming space-time. So yes, let's just get into it. So the structure of this talk, in part 1, I'm going to introduce the basics of space-time and the basis for this thing that's called conformal space-time algebra. Another word for conformal space-time algebra is twistor theory. We'll look at tools for animation and in particular Gaussian splatting coming from this. Then look at tools for electromagnetism and tools for cosmology and spacetime, which is the thing that conformal spacetime algebra was originally developed for about 20 years ago. I say okay, you could take it back to sort of 1905 when people were thinking about conformal transformations of spacetime immediately after Einstein discovered his stuff. You could think about Roger Penrose in the 1960s, but the particular way that we'll be thinking about conformal transformations of spacetime is relatively recent. It goes back to about 2000, 2002. All right, so part 1, basics of spacetime and the basis for conformal spacetime algebra. So spacetime. Here is a graph that you might see in any newspaper or website. This happens to be a graph of unemployment over time. We're all very used as citizens to seeing stuff like this. If you're not familiar with how spacetime works, I'm just going to point out that you would be very, very weirded out if you saw a graph like this do something like that. What would this mean? It wouldn't mean anything is the answer. It's stupid. This really does make no sense. Because in space-time, things don't behave like that, certainly so far as anybody knows. Which is, it kind of tells you that circles are not a very natural object to see in a graph of something happening over time. Same with rotations as well. So you just don't get rotations around points in space-time in the way that you do with points in space. Points in space, you see rotations around, or lines in space, you see rotations around all the time. Very frequently. Yes, so circles and rotations are not a natural geometry for, not natural geometric objects for space-time, but they are for space. This is a more natural thing to see. All right, so here, if we took that point around which this rotation goes, you could imagine doing this, and there's a strong sense in which this particular curve that I've drawn here is associated with this point. It might not be very obvious, but this pair of curves, these are called hyperbolas, and they are associated with essentially the space-time version of a rotation, which is called a boost. And hyperbolas really, really are amazing. A lot of this talk, I remember being in school being shown a hyperbola for the first time, and I mean, okay, circles were obviously very fundamental, straight lines were obviously very fundamental. Ellipses, I guess, fine. Parabolas, also fine, because that's, I throw a rock and it goes in a parabola. Hyperbolas, people are like, oh, why would I care? I thought, oh, why would I care about hyperbola? But now, hyperbolas are my life. I've even got a hyperbola on my hand, I'll show you in a second. And I also want to say that in ordinary discussion of space-time, we have time going upwards instead of going to the side. So that's another thing that you want to think about when looking at pictures in this presentation. All right, we want to think about the geometry of space-time for various reasons relating to physics and computer graphics, electromagnetism as well. And a really useful thing for thinking about space generally is conformal geometry. And conformal geometry, one way of defining it is to say that it's the geometry made from sphere inversions. So this is a sphere inversion. You have this sphere set up, and you say, okay, I'm going to invert this point in this sphere, and it gives you this point. And it's exactly the equivalent of reflecting an object in a spherical mirror. I'm sure you've seen spherical mirrors from time to time. Maybe you've even got one in the wing mirror of your car. It turns out that reflections in spheres have the interesting property that they preserve angles. I'll go into that in a second, but Yeah, inversions in spheres and conformal geometry turns out to be a very, very fundamental thing going on in geometry, especially because reflections in lines and reflections in planes are a special case of reflections in spheres. A line or a plane is just a sphere that's become infinitely big, or a circle that's become infinitely big. And you can do lots of geometry of relevance to engineering, but that involves, rotating things, getting the distance between a point and a plane, all of that kind of stuff, and very easy to do it with conformal geometry. And conformal geometry is very widely applied as well. So here's a picture that I like from my own field of computer graphics. If you've got this thing and you want to turn it into a sort of hat shape, you can see that this thing on the bottom is much nicer than this thing in the middle. Any computer animator will look at this and tell you that this one is better. And that's because this thing is worked out using conformal geometry by a guy called Keenan Crane. Over here, we've got a picture of a toroidal vortex, which is a very fundamental thing in fluid dynamics. A toroidal vortex is when you've sort of got a circle and the air is kind of circulating around the circle. So it's kind of a conformal version of a rotation around a line. This is something called a Smith chart, which is very widely used in electrical engineering. I don't know how, because I'm not an electrical engineer. But yes, very important thing that apparently all undergrads have to learn about. And then this thing down here is a holomorphic function, which is widely studied in mathematics, complex analysis, modular forms, I think. And conformal geometry is very closely related to, yes, all of these things. So sphere inversions, they're not just some sort of curiosity. They're very, very important. All right. And we want to think about the geometry of space-time, and there is a sense in which the geometry of space-time is not about inversions in circles and spheres, because circles and spheres, as I just said, not very natural things to think about in space-time, but they're inversions in hyperbolas and things related to hyperbolas. And here's a ring. This is my wedding ring. I was very pleased to find that this is available. And it has the interesting property that if you look at your reflection in the mirror and I turn the mirror to the side, your reflection rotates. When you rotate your hand, when you rotate the mirror, the reflection rotates twice as fast. Okay, and here's the really important part. So here is a bunch of pictures from Roger Penrose, Stephen Hawking, Wolfgang Rindler. These are all pictures of stuff that you're supposed to understand that's going on in space-time, and you can see some hyperbolas in here. Yes, one or another kind of hyperbola. And yes, it's just very, very important to understand these things if you want to see what's going on with space-time physics. All right, which is most of physics. All right, and the mathematical tool that we're going to use to think about pseudo-inversive geometry, that is reflections in hyperbolas, which is going to give us the geometry of space-time, is to use Clifford algebra. And so a little recap of Clifford algebra. A plus B, if A and B are elements of a Clifford algebra, is some kind of equal mixture of A and B. So if A is a plane and B is another plane, then A plus B is the plane that's in between them. AB is a composition of the transformations A and B. So again, if these are two planes, then reflect in this plane, then that plane, and that gives you a rotation around the line that is the intersection line of the two planes. A versor, technical term, is a transform composition of grade 1 transformations, also known as reflections, also known as vectors. So the vectors of the Clifford algebra that we're going to be thinking about are generalized hyperbolas. So that means hyperbolas that go like this. Well, you'll see them in a second, but transform composition, grade 1 transformations are the most basic transformations. So they're the reflections. And a series of reflections, that'll give you a versor. A blade more or less is another word for a geometric object, like a shape, right? Like a line or a circle or a sphere. All of those things are also transformations. But a blade is a a wedge product of vectors, which means I've taken a bunch of vectors, so that would be planes and spheres and things like that in our case, and I've intersected them. I've taken their transform composition, and then I've taken a single piece of that transform composition, which is going to be the most specific piece of that transform composition. So it might be if I've got plane, plane, and another plane, and I take their transform composition, then I can extract out of that a single point, which is the point where the three planes meet each other. Finally, if I have a transform M, I can apply it to any object B using this thing, MB M tilde, which means essentially the inverse of M. And if we've got this thing CLPQR, what that means is that we have got some basis reflections that square to 1, and those will be, I'll have P of those. I might have some basis reflections that square to -1, and that's what Q would represent. And I might have some basis reflections that square to 0, and that would be R. So if R is equal to 2, then I've got two basis planes that basis reflections that square to 0. All right. So the way we're going to get to conformal transformations of space-time is we start out with CL3, 1, so 3 basis reflections that square to 1 and 1 basis reflection that squares to -1. That gives you space-time. That is, what is it called? The Minkowski metric. Plus, 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 minus. That is the thing that people call it. And for no apparent reason, we're going to put we're going to add 1 to the P and add 1 to the Q, and that's going to give us CL4, 2, and that is conformal transformations of space-time. That sounds a bit weird, so let me say why exactly you would take this particular step. Well, I can't say exactly why. It'll take a long time to say why, but I can at least give you another example of a place where you might have seen this. So CL3, 0, does basic 3D geometry. It's 3 reflection planes through the origin. It allows you to do rotations around the origin, reflections in planes through the origin. And then this, CL4, 1, is more like advanced 3D geometry. So this does inversions in spheres anywhere in 3-dimensional space. And this thing that we're doing, where we're adding 1 to here and we're adding 1 to there, this is called adding a Witt pair, which is an established thing in the literature. It's not even specific to Clifford algebra, so I won't go into Witt pairs specifically. But I will say that within this, I say that CL4, 1 lets you do advanced 3D geometry because it allows you to do 3 different kinds of very interesting geometry. So you've got hyperbolic geometry, elliptic geometry, and parabolic geometry. Here are some really cool pictures made by my friend Royce Nelson. And this is elliptic geometry, parabolic geometry, hyperbolic geometry. A special case of parabolic geometry is Euclidean geometry. Euclidean geometry is just when things move around. And yeah, you get to do all of these 3 things inside of this guy, which is very, very powerful. Yeah, and that geometric fact corresponds to the fact that these 3 Clifford algebras are subalgebras of this Clifford algebra, which is to say you could take a few small pieces of this one and construct one of these 3. All right. So going back to space-time, so here is space-time, another word for it is space-time algebra. It's another word for it is 3 + 1 dimensional, 3 + 1 dimensions, 3 dimensions of space, 1 dimension of time. If you do the same thing to this, you get advanced 3D, 3 + 1D space-time geometry, and that contains, just as the previous one contained 3 kinds of spatial geometry, so that was hyperbolic, elliptic, and parabolic or Euclidean. This has what you call anti-de Sitter, de Sitter, and Minkowski geometry. And if you know, obviously these are just names if you've never encountered them before, but you might have encountered the word cosmological constant. And these are 3 different these are three different kinds of universe that you get with different values of the cosmological constant. One way of summarizing what this means is that in de Sitter space you wrap around in space, which is to say, if we were in de Sitter space, if I go really far in that direction, I'll eventually come back from this direction. All right, so space wraps around, but it's infinite in time, so there's no Big Bang or Big Crunch. In anti-de Sitter space, the opposite is true. It doesn't wrap around in space, but it wraps around in time. If you wait long enough, you'll return to the present moment. And then Minkowski space is infinite in time and infinite in space. Another word that people use for this is that they're all curved in different ways. Something that was rather confusing to me learning about this was there's two different kinds of curvature that physicists talk about. There's cosmology kind of curvature, which is like large-scale curvature. So this is supposed to be a picture of the universe, and if I zoom in on a piece of it, I get this. If I wanted to think about the detail of the universe, I'd use general relativity. Actually, I wouldn't do that because I've never studied general relativity. But general relativity, of course, comes from this guy, effect of gravity on space and time. The large-scale curvature thing is also that guy working alongside this guy who is Willem de Sitter. Normalized verses of different Clifford algebras will preserve different things. So this is one of the most basic Clifford algebras. It preserves distance, it preserves angle, it preserves the origin point. So there's nothing you can construct with just from here that will move the origin or will change the distance between things or change the angle between things. This is a slightly more sophisticated Clifford algebra. It preserves distance and it preserves angle, so it's got rotations, translations, rotoreflections, screw motions, blah blah blah. Here's an even more sophisticated one, and this does all the conformal transformations of three-dimensional space. It preserves angle. That's actually another way of defining a conformal transformation. And a further way of defining a conformal transformation is that it sends spheres to spheres. It sends spheres to spheres. Yeah. And there's something else called Lie sphere geometry, which is actually also based on this similar conformal space-time algebra thing, and that preserves these things called principal lines of curvature. So it's very related to ellipsoids, which will be of use in section 2. But this is we're usually for most of this talk we're thinking about CL4,2 as a thing that transforms space and time, whereas most of this slide is about space. All right, you can think about preserving things in space-time as well. So here's another Clifford algebra, and it preserves, once again, the origin space-time point, and it also preserves, what's the word? Energy. It preserves the angle, the space-time angle between space-time trajectories. So if you've got some object that's moving like this, and some object that's moving like that, then the technical term for it is rapidity. Well, we'll get to it. There's a thing that's similar to angle in space-time that is preserved by this Clifford algebra, and you also cannot move away from the origin. If you have a Clifford algebra, I mean, this is a standard picture that all physicists understand. You've got space, you've got time, and then you've got this thing called the light cone. And Clifford algebra just allows you to say, I can define lines and planes passing through that event down there, and those can be basic elements of my algebra. There's something else, which is in the same way that the previous slide, the next step was to move the origin, but keep preserving your space-time, your angle. This preserves that squared interval, and it also allows you to move away from the origin. So this Clifford algebra will allow you to do rotations, boosts, and also translations through space and time as well. And another way of saying what both of these things preserve is that the technical term is orthochronous. So if you've got a series of events through time, so a photon being emitted, the photon colliding with something, the photon being absorbed, so you can like change things around a little bit. You can change the amounts of time between these things according to different observers. You can also change their order. You can reverse the order, so we can go from it being the case that the photon is absorbed and then it collides and then it's emitted, which sounds a bit strange, but absorption is emission in happening backwards in time, so that's fine. So these are actually sort of more or less describing the same situation. But this is a thing that cannot happen, or rather, it's a thing that won't. There's no transformation that you could do that would turn this thing into this thing. So this is not allowed, where a photon is emitted and then it's absorbed and then it collides. Like, that doesn't make any sense. And we're thinking about an even more sophisticated but even more relaxed set of conditions. We're thinking about conformal transformations. So the angle is preserved, but under a limited set of circumstances, this can sort of happen. Another way of saying, again, this thing that we're preserving is that it preserves E equals mc squared. E equals mc squared is a sort of popular science version of the proper equation that is the relation of momentum and energy, which looks like this. So it's E squared minus P squared C squared equals M squared C to the power 4, which is a much scarier looking equation. If you can simplify this equation a bit by saying the speed of light is 1. You could just choose some units where that is the case, and you end up with this equation, which says E squared minus P squared equals M squared. And in that situation, and this is actually the equation of a hyperbola, which is kind of suggestive, all right? And equivalently, you could say that the transformations of this Clifford algebra send light cones to light cones. So we can move our light cones around, things will be transformed, but there's a light cone will always stay as a light cone. You can't bend a light cone or anything like that. Okay, we're moving on to the basis now. So here are some basis elements of our algebrao geometric system. So this is the E1. So we're thinking about conformal transformations of 2 + 1 dimensions now. All right, 2 dimensions of space, 1 dimension of time, because we want to be able to see space-time. Our eyes are pretty limited to 3 dimensions, and so we're going to throw away one of our spatial dimensions. We've got E1 and E2, and those are going to be doing reflections in space. So you can reflect this way in E1, you can reflect that way in E2, and then this is time, and we can reflect in time as well. Yeah, so time is going up and down. Yeah. All right, and now here is what this thing, another element of our algebra, which is called E plus, looks like. E plus is a hyperboloid. Another word for it is a space-time sphere, or a positive space-time sphere. Yeah, in some sense, it is every point on this hyperboloid, every point in space-time that's on it is the same momentum energy away from the point at the center, which is to say that it's the same distance. The space-time version of distance from the center is the space-time distance from the center is preserved for every point on this hyperboloid. All right. Here now, that shouldn't be a capital E. Here is E minus. And I want to say that both sheets, they're called, are included in E minus. This is another space-time sphere, but this one has got a positive radius, this one has got a negative radius. That sounds very strange. Obviously, in this universe, in the space that we're used to, your sphere has a positive radius and that's it. Well, in space-time, you can have a negative radius. You just got to get used to it. And then this is a space-time sphere with a radius of 0. An ordinary spatial sphere with a radius of 0 would just be a very, very small sphere. That's it. It's funny with this one, a space-time sphere, it's still extending out of that point. But this is a 0 radius space-time sphere. And it is a light cone as well, which is a very fundamental object anybody will tell you in thinking about space and time. And we've kind of gotten it by mixing together these two, so it's sort of in between them. Alright, so here's the sort of group photo of all of them. It's kind of nice, once you get over the positive and negative radius thing, it's nice that all of them are visualizable. That doesn't actually happen with conformal spatial geometry, because it turns out that you actually do have a negative radius sphere in conformal spatial geometry, but the negative radius sphere is unvisualizable. Another word for it is a hyperideal sphere. But yes, there they all are together. And now we can build some objects out of them. So this is E plus T. So it's the intersection of ET, that's this plane here, with the hyperboloid of one sheet, which is, and it gets you that circle there. So that's E plus T. Here is the intersection of E2, that E2 plane, with, again, E plus, which is the hyperboloid. So it gets you this hyperbola pair. Here is E2 minus. So once again, it's both of these. Both of these hyperbolas are included in E2 plus, and both of these hyperbolas are included in E2 minus. And there's E1 minus and E1 minus and E plus, E2 minus. There's E1 minus and E1 plus as well, but you can figure out what those are. Here's E12. It does an ordinary rotation. Here's E2 plus T. Right, yeah. So this is the intersection of E2 plus with ET. So ET is that, aside from being a little alien, ET is the plane that's like this. It's the time plane. So if you intersect these two yellow lines with that plane, then you get these 2 points. That's E2 plus T. And there's E123. It's worth saying that, here this thing which has got 3 downstairs indices is a pair of points, whereas this one looks like a single point. This single point is actually sort of partnered up with another point, but it's a point that's infinitely far away. It's the point where these 3 it's the other point where these 3 planes meet, which is a strange thing to think about, but yes, you can eventually get used to it. Alright, so that's the end of section 1, so I'm going to check the chat now. STA does preserve space-time intervals. I haven't drawn E plus plus E minus, that is true. Jeff is asking about how there's E plus plus minus E minus, yes, you could ask for E plus plus E minus. That would be, so look, we've got these 2 guys, and we've mixed them together, and that's brought them both in towards the center. So if you mix them together, but with one of them going in the other direction, that'll take them out in that direction. And so E plus plus E minus is the light cone at infinity, which is a weird thing to think about. But yeah, another word for it would be the Big Bang in Minkowski space, but you don't necessarily want to think about that too hard. You don't need to. Anyway, these things will get you a long way with what I'm about to say. So, but yeah, there you go. All right, so we're going to think about computer animation for a second. For a few minutes. So, animation and rendering of Gaussian splatting particularly. So, Gaussian splatting, an approach that people are using more and more to rendering. So, this picture, amazingly, is not a photograph. It is a rendered image. It has been created by if you were to zoom in, you would see that it's made out of lots and lots of little ellipsoids, is the technical term for these. And conformal spacetime algebra, CL 4,2, is useful for ellipsoids. You can represent an ellipsoid this way, and you can represent a ray in this way. Oh, by the way, I mean, so you've got to kind of take all of this and bring it up a dimension, which I appreciate is not that easy. But so this circle would, if you added a dimension, would become a sphere, and if you tilt the ET plane that was used to acquire it, then instead of being so it would be an intersection of this shape with a plane that you've tilted, and so instead of being a circle, it'll be an oval. So just as you can get a ellipse in two-dimensional conformal spacetime algebra, you can get an ellipsoid in 3+1 dimensional conformal spacetime algebra, and you can get intersections with ellipsoids with just a wedge product, so one line of code, which is very nice. The way that I haven't developed an algorithm for this, I need to work on that, but I'm just saying that this is a potentially promising research direction. If you look at the way that people are extracting ellipsoids today, in the case of this one, this is from the wonderful Inigo Quiles, and he calculates it here by doing an iterative thing. That's why he's got a warning here saying that it's not exact. So it's an iterative process, which is not a great thing. So you can. It's a lot better if you can just call one function and there's the intersection of the ellipsoid. Similarly, here's somebody else's approach to it, and they do manage to get it. They have a non-iterative process for doing it, but they've still got to call a transcendental function. They've got to take a square root down here, and have an if statement as well. And you don't really have that. You don't have that in the same sort of way if you use conformal spacetime algebra, because what happens is that you get these points as little pairs. I'm thinking that then you do a comparison on all of those pairs. You choose the one that you care about the most, which is the one that's closest to you, and then you can extract the position of that one, which does involve a transcendental function, but it avoids you having to think about the transcendental. It means that you're not doing a transcendental function for every single ellipsoid along your ray. Instead, you're only doing it for one of them. Okay. And here's just a little demo where I have rendered an ellipsoid and other things in conformal spacetime algebra. So what we're doing here is that we are smoothly going between right now. So you saw a sphere there, and that is 3 dimensions. That is just a 3-dimensional slice of the 4-dimensional thing, 4-dimensional hyperboloid. But if we look at this moment, that is a space-time slice. So it looks more like a hyperboloid. And then in the middle there, it briefly becomes a cylinder. And I haven't cracked rendering it as a cylinder. The cylinder situation, which I'll talk about in a few minutes, is the case of a light-like visualization. So you're thinking about what the universe looks like from the point of view of a light ray, which is a strange thing to think about, but apparently quite useful. Okay, you also get this is a useful thing for computer animation, you also get non-uniform scaling. So non-uniform scaling is something that computer graphics practitioners would often think of as a very easy thing to have, and in some senses, of course, it is very easy. You just take your coordinates and you multiply by a scale factor in this direction or whatever. It's not quite as simple as all that, because maybe you want to apply your transformation to different kinds of object. Maybe you want to interpolate your transformation in a way that preserves volume. That's why I've got this picture here. So animators really like preserving volume. And what we've got here, we've got this is on the right here. This is sort of like properly animated, following Disney's principles of animation, where the ball bounces and it goes down, but it squashes outwards. and then it bounces up again, and yes, squash and stretch. That's nice. Whereas this one is like the amateur version of the animation, and interpolating is something that is done very nicely. That can be done very nicely using Clifford algebra, and in fact, that's why Crytek and Disney use the little bit of Clifford algebra that they do use for animation instead of matrices. That's called slurping. So spherical linear interpolation. Spherical is a misnomer, but yeah, it's a kind of interpolation. So slurping. And yes, you can use conformal spacetime algebra to slurp a non-uniform scaling. Yeah, here's a picture of trying to interpolate a matrix, and it doesn't do volume preservation. Whereas if you use quaternions, you do get the right thing, and that's why the games industry shifted to using quaternions. But yes, Disney and Crytek, it's a bit of a bargain when you start using Clifford algebra for this kind of interpolation, for the kind of interpolation that they're doing, because you lose the ability to use non-uniform scaling, but conformal spacetime algebra brings it back, I think. Haven't tried building a game engine on it. Alright, so that's it for... Oh, and just to say that about that, this also might be good in terms of animating sets of Gaussian splats, because it seems, well, people are probably going to want to animate Gaussian splats sometime soon. They're very, very big, and so you want to have some, like, persistence from frame to frame. So let's say that my arm is made of Gaussian splats, and let's say I want to move it to here, and it's still made out of Gaussian splats, and it's the same set of Gaussian splats. Finding the animation that interpolates from here to here is a nice thing to be able to do, and a good thing. A good way of doing it would be to like average average the transformation that takes this Gaussian splat to this Gaussian splat, that Gaussian splat to that Gaussian splat, blah 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 blah, and then calculate that offline, and then render it on the client side when it's time to do that. Yeah, blah blah blah. So we're interested in conformal spacetime algebra objects for electrodynamics. Electromagnetism is invariant under spacetime conformal transformations of spacetime. This was noticed, like I say, just after Einstein figured out enough about, well, made it so that people could notice it. All right, so you've got here is a very important object in electromagnetism. This is a dipole, and the field that's induced by a dipole looks like this. And that field, in some sense, corresponds quite directly to a versor of conformal spacetime algebra. It corresponds to a versor of ordinary spacetime algebra as well, but I'd say that this one is kind of better, because this E1 minus is immediately interpretable using the thing that I showed you earlier. Same with this thing. So if you've got a magnetic field that has this that's characterized by this looped wire, yeah, you've got that as a versor as well, and E1 plus is that particular circle there. Here's a lovely animation on Wikipedia that was made by this person called Geek3. Well, that's their screen name anyway. That shows you going between the two of them, and it's really interesting to think about this because, because these are both bivectors, and you want to be able to go from interpolate from one bivector to the other, and this allows you to do that. But it does strange-looking things to the field, but this would usually be considered a bit strange. And by the way, so right now you want to think about that sort of point and cross. That's a loop that's just been cut this way. And in between, it has become a zero radius circle, or that is a zero radius point pair. there's a term in that a term for that in electrodynamics as well, which is a magnetic dipole moment, which you use as a sort of probe to derive an equation for the magnetic field at a point. So that's a useful thing to have as well. A zero radius circle. Strange sounding thing to have, but it's an object in conformal space-time algebra, so you're happy that it's there. Here are some results that other people have come up with for relating to this. So Martin Rolfs here presented some research he's done with Stephen DeKennick that gets a unified Lorentz force law. Very, very encouraging. But on the other hand, this paper showed that things get very, very complicated if you want to do non-trivial things with electromagnetism with conformal transformations. But I think possibly the problem that they had here was a problem of representation. At least I'm hoping that. The thing that you have here is strictly Minkowski space, so it's this thing space-time algebra projectivized. CL3, 1, 1, 3 basis elements squaring to 1, 1 basis element squaring to -1, 1 basis element squaring to 0, and we'd think of this as the subset of conformal space-time algebra where things are flat, where you've only got the E1, E2, E3, ET, and the light cone at infinity. Whereas, hopefully whatever results that these two get can be generalized to de Sitter space and anti-de Sitter space from Minkowski space using conformal space-time algebra. We'll see. All right, here's another useful thing in electromagnetism. So this is called the Kelvin transform. So you're taking, in this case, a fluid flow field, and you are confining it to this small area. Like the thing that you start out with is an infinite domain. You perform that transformation. You've got it in a small domain. You solve things there, which is nice to be able to do because it's limited. And then you map it back again. And this is a transformation that can also be done in conformal space-time algebra. I guess it's nice because it also allows you to solve a problem over an infinite domain of time, as well as an infinite domain of space. Here's another useful thing. So this is from electromagnetism. You've got something called a Leonard-Vichert potential, which is how you calculate the the field induced on a point by a moving charge, and that is that's what a Leonard-Vichert potential is. And because light cones are null vectors, light cones are I showed you an example, E plus minus E minus. You can just take a wedge product with the trajectory here. At least assuming that the trajectory, at least if you've got a part of the trajectory down here that is locally a hyperboloid, which should be hyperbola. You can intersect a hyperbola with a light cone and get this thing down here. So you want to be able to do that. So a light cone, I already said it's a zero radius hyperboloid. So here's a hyperboloid. If you tighten, you get a light cone. All right. And this is speculative, but something I see people talk about called a mass shell. I don't really understand exactly what it does, but it's hyperboloid. It's shaped like a negative hyperboloid, so it's certainly going to be an element of conformal space-time algebra. The thing that people point out, though, is that it's not an object in space-time. It's more an object in momentum space. I don't exactly know what that means, because it seems to me that momentum is in space-time, but anyway. Yes, and, we could at least... It's nice to be able to apply boosts and translations to a mass shell, I would think. So maybe that's a good thing to have, regardless of whether it's in space-time or not. And you can get this from conformal space-time algebra. Okay, part 4, conformal spacetime objects for special relativity and cosmology. So, physical trajectories, that is, trajectories of any physical object that you can consider, are, well, I said it a few slides ago, they are locally approximated by hyperboloids. A straight line is a special case of a hyperboloid, by the way. So this one in particular is a null geodesic. That means that it's a light-like trajectory. You get those, of course. You get those in spacetime algebra projectivized as well, but in spacetime algebra projectivized, you do not get hyperbolas, whereas in conformal spacetime algebra, we do get these things. So if you've got something that's accelerating at a constant rate, then its trajectory will be, an object in spacetime. An object. Its trajectory is a blade, all right? It's a trivector. You also get stuff like this. So these look like they're trajectories, but they are not trajectories, probably, unless you believe that virtual particles really exist or something like this. I have no stake in that debate, but this is an object that, you couldn't really ever go along this trajectory. They are blades in conformal spacetime algebra as well. And that might sound like a bad thing, but no, it's good. It's good to have these because they do a different job. The job that they do is that they are the axes of a boost, or a boost in de Sitter or anti-de Sitter spacetime. Okay, back to this kind of picture for a second. If you have a reminder that the hyperboloid of one sheet is E+, and then this thing here is E-, and if you take the intersection of those, you get this pair of circles at infinity, and this corresponds to something that is apparently talked about fairly frequently, at least by Roger Penrose. It's called light-like infinity, or null infinity is another word for it. Quite an interesting object. This is Rindler coordinates, and these are easy enough to do in conformal spacetime algebra as well. There'd just be a light cone added to a multiple of E+, and that's it. Here's something. There's something called a Rindler horizon, which is related to a very, I don't know when it was proposed, but it's something that people would still like to do experiments with, this thing called Unruh radiation. So a Rindler horizon it's kind of like the event horizon of a black hole, so the part of a black hole that you'll never get out, such that you'll never get out of the black hole once you've gone past it. But a Rindler horizon, it's like a little fake black hole that you can bring into existence by just having a constant acceleration. Which sounds very strange, but yeah, so if your constant acceleration would mean that you've got a trajectory that looks like this, and then this red thing here, that would be your Rindler horizon, the Rindler horizon of the thing moving at that, moving with that acceleration. And Unruh radiation is the proposal that a horizon like this would radiate according to the observer, I suppose. And by the way, this hyperbola is tangent to both of these blue planes. If the thing to imagine here is that you've got like a creature in 2 dimensions of space, 1 dimension of time, and they're sort of going up like that. They maybe measure radiation coming from this horizon, from the blue plane, which they can perceive. But like I say, there's no experimental confirmation. Well, there's debatable experimental confirmation of that. The way that it looks in 3 dimensions is something like this. So here's your 3-dimensional creature. They're at this location. So this is a green point in space. And that will look like this in space-time. If you cut away one of the spatial dimensions and replace it with the time dimension, the blue plane is sort of coming towards them. It looks very scary, like it's a monster trying to eat the poor little child. But the the nice thing about a Rindler horizon is that you can make it cease to exist by just stopping. And space-time algebra projectivized does it's able to represent this horizon. It's able to represent this red line, and it can do them in Minkowski space. Conformal space-time algebra can do them in de Sitter space or anti-de Sitter space, which STAP can't. But STAP again does not have this green hyperbola. And that hyperbola might be a nice thing to have in your coordinate system from which you could immediately calculate, or very, very quickly calculate this red line here. Incidentally, this has the, I think, yeah, this is well known, but it's very disconcerting. Hyperbolas always come in pairs, which means that when you have a constant acceleration, creating a Rindler horizon, there's a kind of mirror image or antimatter copy of you. Oh, I don't know if it's antimatter, but some kind of copy of you on the other side. Very strange, but yes. So these two green hyperbolas are both tangent to this pair of blue planes, which meet at this red line. All right. Penrose diagrams / causal diamonds / conformal diagrams. These are very important things for thinking about general relativity as well. I, again, have never done general relativity, but there's lots of them in textbooks. You will notice that these curved lines here, those are all hyperbolas. And since we are great at hyperbolas in conformal space-time algebra, you would think that we can do them. And indeed, we can do conformal diagrams. Here's a conformal diagram from a different textbook. So when you have an ordinary causal diagram, you end up being tempted to postulate the existence of parallel universes. Maybe a little bit like this sort of thing here. But, you know, I do see people, like there was a Veritasium video sort of saying, oh yeah, it's a parallel universe and it maybe got different things going on inside it to the universe that we've got. You might think that that's a little bit ontologically extravagant, let's say. And so the way that conformal spacetime algebra lets you do things gives an answer, allows you to kind of see, well, I dare say, see what's going on, really. You don't have to postulate the existence of a parallel universe. So I've got the simulation running here. So this is a universe, a little universe that's a de Sitter universe. So it's got I'm sort of cutting off the cone up here, by the way. So this is the beginning of time, and then it's evolving forward to the end of time. Like, you can think of this sort of grey sheet as a sort of cloud of matter. It all starts off at the Big Bang, and then it goes to the Big Crunch. And it's kind of always attached to this diamond in the middle. This diamond in the middle is the 2 + 1 dimensional version of a conformal diagram. Yes, and note that you've got the part of the sheet that's sort of inside the causal diamond, and everything that happens outside of the causal diamond is completely determined by what happens inside of the causal diamond. So, yeah, you don't have to believe in another universe where different things are happening. It's just a mathematical artifact of what's going on in this universe. Like, the outer part of the sheet is, again, completely just determined. It's a residue of what's happening to the inside part of the sheet. All right, moving on. Entanglement. One of the frontiers of modern physics. You've got an event where two photons, we're going to choose photons initially, are entangled. This is speculative now. I'm not very certain of what I am certain of the maths of what I'm about to say. I'm not certain whether it corresponds to entanglement, but I'd like to investigate it. So you've got a space-time point where two photons are entangled. these are, let's say, their trajectories. They are lines going up the null cone. So these are null lines. You've got two flatlanders, Alice and Bob. They measure the polarization of the two photons, and they get really interesting results in their experiments, which humanity would like to know more about. And, you know, it's the thing that's sort of suggestive to me, let's say, is the fact that it's kind of like you can kind of think once you've got their polarization up here, you can kind of think of it as going as you'd tend to think of it as always having been there. That depends on your interpretation of quantum mechanics or whatever. But you know, the polarization is something that goes along this trajectory of this photon for sure, in the usual sense. And note that the photon trajectories, just these two lines on their own, are a single blade of Cl4,2 in the coordinate system that I've shown to you. So, and let me be clear about that. This line and this line are together a single blade. It's not like one blade for this line, one blade for that line. No. It's one blade, because you could take a plane and intersect it with that null, with the light cone, and you would get that sort of cross. So crosses are null. They would be trivectors of Cl4,2, 0. And then this sort of combined rotation that's going around the two lines, that is also, well, that's a versa of Cl4,2. And these are two commuting objects. This blade commutes with this versa. Does it commute? Yeah, well, it's got an appropriate relation such that they are sort of compatible geometric objects. To me, that's suggestive. I don't know. You can do the same thing. I chose photons, so that's trajectories on the null cone for this. If you do the same thing for objects which aren't moving at the speed of light, so objects that aren't photons, for example, to electrons with spin, which you can also entangle empirically, you would get something like this, and that is a bit, I'll say, weirder. That you'd get this for your blade, and you know, this would raise all sorts of questions like what would be measured here by somebody. It's not like, you know, famously, whatever your interpretation of quantum mechanics, it's probably not the case that you know, information is traveling faster than the speed of light. It's probably not the case that Alice measures her photon / thing and it sends a signal to Bob's thing. Like it would suggest that there's information going back in time for sure, which I appreciate is bad, but you know, it's interesting to me that this is a geometric object. This is again a versa of Cl4,2. And yeah, I'm interested in interpretations of quantum mechanics. I'm agnostic about which one is true. But these three very intelligent people, and very famous in the case of Gerard Tufte, would say that we should change our conception of time based on the results, that the empirical observation that entanglement is a thing / Bell inequality violation is a thing. So yes, I'm not saying I know how we should change our conception of time, but I am saying I want to be able to think about space and time as well as I possibly can, given that pictures like this are supposed to be invariant under trans boosts and that kind of thing. So I want to be able to think about what it means to say that there's an observer who sees Alice's measurement changing Bob's measurement, or vice versa, or something like that. Yeah, I want to understand that. And I think that this is a good bit of mathematical machinery that lets us do that. All right. So Robinson congruences, these are little copies of 2D CGA inside of conformal space-time algebra. Sorry, I've kind of put the cart before the horse there. Robinson congruences are a thing that Roger Penrose used to invent/discover this thing that we call twistor theory, which is more or less conformal space-time algebra. He was sort of saying, when you choose one point in space-time, it's kind of like you've got a Riemann sphere around that point, where a Riemann sphere is kind of like the complex plane. And he built up, he built up twistor theory in this particular way, and we'd like to have an understanding. If we're going to claim that there's a connection between twistor theory and conformal space-time algebra, then we want to understand what's going on here. The Riemann sphere it basically is conformal, 2D conformal geometric algebra. So that's spatial conformal geometric algebra. And the way to think about this is, if you've got a clue as to how we can think about this is, you choose a light cone, you choose a null line on that light cone, you choose a particular plane that is orthogonal to that light ray, or appears to be orthogonal. You can choose, once you've chosen that plane, and here's a few different choices of planes, you get a single point in space-time, and this should remind you of this picture from Eric Lengel, where you've got the null code. You build up a picture of 1D conformal geometric algebra using your null cone and your horosphere, which is like a parabola. This yellow plane is like the blue planes that we've got there, and the horosphere gives you one copy of 2D CGA, and then what you find is that along a light ray you've got a series of copies of 2D CGA, which is to say that you've got a series of copies of the Riemann sphere. But I have to say, the next thing that Roger Penrose always does, having shown this picture here, he then gets up this picture, and I don't understand what the connection would be, because I do understand this picture. This is a Hopf vibration / Clifford parallels. But yeah, I don't see how it connects to 2D CGA, but working on that. All right, the product of two light cones is a projector onto one of them, and a projector can be used to make spinners, and spinners of conformal space-time algebra are, it is claimed by Chris Doran, twistors. So it would more or less look like this. You get these two, your axis is these two hyperbolas, and your transformation kind of pulls you onto this light cone here. You could multiply them in the other order, and it would reverse the direction of these arrows. Also, uniformly accelerating mirrors is something that people have been investigating experimentally in the last 20 years. They've gotten some apparently interesting results that I don't understand, but I'd like to understand. And I'll just say that uniformly accelerating mirrors are, again, very simple objects in conformal space-time algebra. They're just the hyperboloids, and you do a sandwich product with the hyperboloid. Another thing that you hear about in theoretical physics a lot is ADS-CFT. And it would seem to me that... So ADS-CFT is supposed to be a treatment of something called the holographic principle, which says that even though our universe appears to be 3+1 dimensional, all the information you seem to need seems to be confined to a two-dimensional thing, the hologram. So that's the hologram of the holographic principle. If you take CL4,2 and you knock off one dimension, you get the conformal transformations of 2 dimensions of space and 1 dimension of time, of course, and that is that's this. So that's your hologram, and CL3,2 is also anti-de Sitter space. So it's yeah, it's a thing that I can that can be visualized using conformal spacetime algebra as well. It's when you have if I go back to my basis at the start, you've got everything in the basis except for E plus. You don't have E plus. You try to do everything with just this and these guys. And then this is the Cartan-Dieudonné thing. So, well, basically just if you want, Cartan-Dieudonné says that you can build up, if you're in an n-dimensional space, you can build up its isometries with n reflections. In space-time, you have something that you might reasonably call a light-like translation. It's not a physically possible thing to do, but it is something that mathematically you should be able to do, and Cartan-Dieudonné is supposed to be a mathematical thing. And I notice that you cannot, if you want to do a light-like translation, you might very naively say, oh, I just reflect in this plane, then reflect in that plane. And that almost gets you the answer, but it doesn't quite. What it gets you is this thing, but this thing is not a transformation. It's not the transformation that you want. Whereas if you take 2 points that are on these two planes, and they're on a trajectory, and you take the transform composition of these 2 points, well, that would be, a point is a pair of reflections, so that would be, point here, reflect, 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 reflect. That's the full transform composition. So 4 reflections, and that gets you your light-like translation. And the result in the representation in the Clifford algebra is a scalar plus a bivector. Simple sounding object, but it's a 4-versor. You've made it with 4 reflections, which is very strange, especially if you're thinking about CL 1,1,1. It seems to slightly contradict Cartan-Dieudonné because CL 1,1,1 is 3-dimensional. But if you really want, so you could fix this bug by saying, light-like translations are not a thing that I want to claim to be able to do. They're not an isometry of 1 plus 1 dimensional Minkowski space. You could say that, but if you really want to if you do want to have that, which I dare say that we do, because we want to move. Yeah, we want to say that the origin is somewhere else along a light ray. Well, you can use CL2,2, and then your Cartan-Dieudonné holds. So, because you can say that it's a 4 reflection, so it's a isometry of CL2,2, whatever. This is the osculating circle. An osculating circle is a way of thinking about curves in 2-dimensional space. Well, you can think about curves in 3-dimensional space as well this way, but only 1-dimensional curves in 3-dimensional space. So yes, this is a circle that's sort of tangent everywhere to this curve, right? Quite a beautiful thing to look at, and this is an animation created by Freya Holmer. You can reasonably, you can take this concept and reasonably ask for, hey, what would it be in 3-dimensional space? And the answer is you'd have a surface, and you have people. I've seen people call it the Cartan hamster ball going around on this surface. So that's an osculating sphere. You can ask for it in space-time. Why not? In which case you get an osculating hyperboloid. And this is, I feel bad because I don't remember who created this picture. I'm just going to look it up. But this is a picture illustrating McDowell-Mansouri gravity, and from a guy called D.K. Wise, Derek Wise. So thank you very much, Derek Wise, for that picture. It's hard to picture in your head, but there it is. You're thinking about an osculating de Sitter space-time, and trying to do general relativity that way. And it's been shown previously that conformal geometric algebra is able to be an instantiation of like the osculating sphere. So this is from a paper by Chris Duran, and you define a sphere here, you define a sphere here, you define a sphere here, and this surface is kind of an interpolation of all of these. And you could reasonably do the same thing with some de Sitter spacetimes at the different points. All right, so here's the list of things that conformal spacetime algebra has maybe unified. Light cones, rotations, translations, boosts, so the Poincare group, dipoles, test charges, magnetic dipole moments, de Sitter, anti-de Sitter, Minkowski, cosmological constant, these different kinds of spaces, Kelvin transform, Leonard-Vichert potentials, mass shells maybe, ellipsoidal Gaussians for computer graphics, entanglement maybe, constant accelerating objects, including mirrors, which are of interest to experimental physicists right now, Robinson congruences, Rindler/Unruh horizons, Rindler coordinates, ADS-CFT, McDowell-Manzuri gravity, conformal diagrams/Penrose diagrams/causal diamonds, and time-like, space-like, and null infinity, and they all end up looking like this. Or at least these are examples of what they could look like. And I mean, look at all this, look at all of the names that are on this slide. Like, this is pretty much, you know, it looks like the index page of a textbook, whereas now it looks like a small excerpt of a Cayley table, right? I think that that's interesting, personally. So thank you very much to Anthony Lazenby, Joan Lazenby, and Chris Duran for advising this project. You can reach me here, interested in any questions, and now I'll look at what is in the chat.